The talk that I was asked tonight, actually I was totally free to decide of the theme, and I decided to talk on something which is, I believe, dramatically not assessed or not studied, which is the link between economics and physics. What I'm going, and the conclusion to which I am going to draw you in a way is that when you put physics into economics, you come up with results that are not very easy to sell in an election. If you look actually at the conventional speech on the question that is raised here, the answer is yes. Yes, you can have everything at the same time. Actually, a body which is called the United Nations, which is supposed to be a serious one, or at least a place where a large number of people should agree on serious things, they tell you that we have sustainable development goals, 17 to be precise, and so these sustainable development goals should be achieved all at the same time. And actually, if you pile them one on top of the other, it's close to Alice in Wonderland. You are going to satisfy economists, you are going to satisfy doctors, you are going to satisfy people that teach something, you are going to satisfy feminists, you are going to satisfy people that drink water, which is quite a great number of people. You're going to satisfy mayors, you're going to satisfy industrials, you're going to satisfy the consumers, do not forget the consumers. Of course, you're going to satisfy people that care about the environment. You're going to, okay, so everybody's going to be satisfied. I mean, this or any pre-electoral speech is about the same. Vote for me and I'm going to bring you happiness. Whoever you are, whatever your goal is. The short answer is no, so we can all go out and have a drink. I'm trying to give you a longer answer during the time slot that I was allowed. And to give you the longer answer, I'm going to go through something which is called energy. You probably know that we have a minister in France in charge of energy matters. Actually, it's been a very long time that we have had in France somebody in charge of energy matters. I'm ready to bet with about anybody in the room that if I ask to the minister in charge what is energy exactly, I will get anything but the right answer. So if anybody is ready to bet, I take all the bets when leaving the room. Because when you ask the question to the general population, and the general population and the minister in charge actually basically think the same way, that's how democracy works, you will get this answer. Energy is a bill. Energy is something you pay, something you purchase, actually. The first thing you're going to think about is your electricity bill, because that's the bill that you receive. Everybody receives an electricity bill, basically, except for tramps that live in the street. The second thing that you might think of, because a number of people have a central heating that operates with gas, is a gas bill. Some very clever people might think of the gasoline that they buy at the pump, but that's it. I mean, energy is a bill. Well, it happens that if you answer energy is a bill, you have just allied yourself with the economist, and it's the wrong answer. It's the wrong answer because if you look at the size of the bill compared to all what we spend, it's a small bill, a very small bill. This curve gives you the fraction of the spendings that are devoted to buying energy. Okay? What it tells is that except during oil shocks, what the world spends on average to buy oil, gas, and coal, and I do not have a curve today, but I remind you that 65% of the electricity produced on Earth comes from coal and gas. So first you buy oil and gas, coal and gas, sorry, is a couple percent of our revenues. So on average in the world, you, we spent a couple percent of our revenues on energy. It's negligible. Okay? In France, you spent 1/3 of your revenue on housing. That's a serious matter. Then you spend 10% of your revenue on food. It's almost a serious matter. Used to be about 3 or 4 times this. You spend a couple percent of your revenues on phoning to a friend saying that you're going to be late. okay? Which is about the same amount of money that you spent on energy. So energy is negligible in our spendings. And because it is negligible, that is, it's a couple % of our spendings, when you talk to Homo economicus, the reflex that he will have is saying, okay, if it's a couple % of my spendings, I'm going to deal with the topic a couple % of my time, and that's it. I'm done with it. Now I can deal with serious things, geopolitics, pension funds, whatever, not energy. Okay, so energy, I take a minister for that, give him instructions, and sorry to say it in French, as de Gaulle said, l'intendance suivra. No big deal. Okay? Well, thinking like this is about as relevant as if you said, my brain is 2% of my weight, so I can take care of my brain 2% of the time, and the rest of the time, it's of no use taking care of my brain. Okay, I can do whatever I want with my brain. It's just, or I can devote to somebody to take care of all the brains, and I'm going to give him 2% of whatever, and I can independently look at the rest with other people. Of course, it doesn't work because our body is a couple system, and if I remove half of your brain, I just do not diminish your weight by 1%. And therefore, you power by 1%. I just kill you. What I'm going to explain is that it's exactly the same thing for energy. Actually, we just don't care about how much it costs. It's just not the point. Okay? We just don't care. Now, let's suppose that we still ask the question. There is a second very common answer, which is when you hear energy, you think savings. Energy is something we must save. Again, it's a wrong answer. If you are all in this room with the time to listen to me instead of growing potatoes, it's precisely because for the last 2 centuries we haven't saved energy. It's precisely because of this. If during the last 2 centuries we had saved energy, there would be 500 million peasants on Earth. No students here, or a handful. Okay? Because it's because of the productive system, the tremendously productive system that we have set up with machines, that we have enough time to do everything else than growing potatoes. Okay? Second wrong answer. A large number of people just have no idea, and it's okay with them, because there is a minister in charge, okay? And if you ask a poet, well, the poet is going to give you what is the closest to the good answer, which is energy is something you're full of a morning that you're in great shape. Well, actually, that's the good answer. Because as you probably know in this room, energy is by definition in physics what quantifies change. So if you are packed up with energy, you are packed up with the ability to change your environment, and that is, you are packed up with the ability to master your destiny. So energy is by definition what allows you to change the environment, by definition. For that, only you need a converter. Of course, you cannot use energy in a raw way. So energy is something that enables you to master your environment. And because of the law of conservation that you probably know better than I do, all we can do regarding energy is actually not produce or producing energy. It is extracting energy from the environment where it is already there and use it into a converter to get something that we deem useful. That's all we can do with energy. Okay? The energy that we get from the environment, we often call it primary energy. So when you read primary energy somewhere, it's the energy that already exists in the environment, namely things that burn, oil, gas, coal, wood, waterfalls, wind that blows, etc. That's primary energy. Of course, part of the primary energy we find into the environment is chemical energy in the form of edible products. That's the first energy that humanity has used, and it has used it with the only converter that was available at the time, that is our own body. So we take that energy from the environment, say kill a mammoth, we eat it, and that gives us enough energy to remain at 37 degrees Celsius and move around so that we can hunt other mammoths. Okay? So that's the first converter that we have at hand. But today, we have, thanks to Carnot, Papin, and others, discovered another number of converters that we can use, and that we can use with other forms of energy than edible products. Those are the machines that surround us today, everywhere, all the time. These machines have enabled us to convert other forms of energy, because when somebody says that you consume energy, actually that's false. You do not drink oil, and you do not breathe gas, and you do not eat coal. Okay? So you do not consume energy. Actually, what you really do when somebody says that you consume energy is that you use a machine that converts the energy. That's what you do. So using more and more energy, you must remove that expression from your heads and think using more and more machines. That's what it means to say we are using more and more energy. It means we are using more and more machines that have a greater and greater ability to create physical flows into the environment. That's what we really do when we consume more and more energy. The amount of energy that we are now able to get through machines is tremendously more important than what our own body is able to provide. My father, among his accomplishments, was also a modest, as I am, mountaineer. So he was once in a while in the mountains, but you can also imagine climbing up the Eiffel Tower, it works as well. So let's assume, for example, that every morning before breakfast, in order to feel in great shape, just as I said before, you climb up, let's say, 6.5 times the Eiffel Tower, on foot, not with the lift. The advantage, of course, is that you have less Japanese tourists when you climb up. If you do this, and if you weigh 80 kilograms plus 10 of your backpack, that's only because the calculation is simple. Of course, what I use is the very basic formula, which is E equals mgh. It's as simple as this. You come up with the conclusion that all that your body can yield in a day's, in a great effort that lasts for 1 day, is a ridiculous half kilowatt hour. Okay? If you use your legs, well, you can use your arms. It's not as convenient. But if you use your legs to climb up 2,000 meters, all you have provided in the form of mechanical energy is a ridiculous half kilowatt hour. Fully ridiculous. If you do this 1 day out of 2, or every day you climb up 1,000 meters, at the end of the year, you're able to provide 100 kilowatt hours of mechanical energy. Okay? That's the order of magnitude of the mechanical energy that a human body is able to provide over a year. If instead of using your legs, you use your arms to shovel up earth, same thing, E equals mgh, you come up with the conclusion that you are 10 times more ridiculous, because with this kind of effort, you will provide 0.05 kilowatt hour over a year of mechanical energy. Totally ridiculous. Totally ridiculous. Okay? In 1 single liter of gasoline, 1 single liter of gasoline, and I remind that in France, we use roughly 1,000 liters of gasoline per capita and per year, despite the fact that we're supposed to be all nuclear. So 1 single liter of gasoline encloses 10 kilowatt hour of thermal energy. And if you put this into a machine, of course you have the Carnot yield, you are going to get out of this machine 2 to 4 kilowatt hours of mechanical energy, which means that in a single liter of gasoline, you've got the same ability to transform the environment that you have in 10 to 100 days of hard human labor. That's what machines mean for us. Now, if you convert this into money, it means that if you take the person that changes the environment, if you hire that person at the minimum wage, okay, the human kilowatt hour is going to cost you anything between a couple hundred and a couple thousand euros, when the machine is going to provide the same service for, I do not count the cost of the machine, for a marginal cost of 10 cents. So going from man to machine is a way to divide by a factor of several thousand to several hundred, depending on the efficiency, the cost of unitary transformation, physical transformation of the environment. Namely, building 1 square meter of housing, that's physical. Transporting 1 ton of goods, that's physical. Manufacturing 1 chair, that's physical. Growing 1 carrot. This is why your purchasing power has increased. This is why you can have negotiation on your wages and believe you're going to win. It's not because your boss is somebody fabulous. It's just because we have had this 2-century increase in productivity due to this. So the only reason why the budget of research has increased is there. And the reason why it's going to decrease from now is there also, we're going to see afterwards. It's physical. It's physical. Now let's suppose that we take a slave. The definition of a slave, it's not very moral, okay? But the definition of a slave is that it's someone you do not pay for his or her work, okay? But generally, it's not something people are very fond of, becoming slaves. So when you have a slave, you have to go and get the slave against his or her will. And you have to keep the slave alive, so feed the slave, give him a minimum clothes. You have to prevent the slave from fleeing because he doesn't want to remain a slave. Prevent him from slaughtering you, if you can. See Django, etc., etc. So you have to pay a number of things when you have a slave so that the slave remains a slave at your service. When you pile up the cost of having a slave, you come up with the conclusion that even a slave is going to cost you 10 to 100 times more money than the machine. And the reason why slavery has disappeared in countries that gained access to a growing flow of energy is just because of this. It's not because your genetic code has dramatically changed and you are good when your ancestors were evil. Your ancestors were as evil and as good as you are. No more, no less. Same genetic code. The difference is there. The difference is that it doesn't make any sense to bother with slaves that want to slaughter you and flee when the machine that doesn't have all this inconvenience and can work all day around, all year round and all day round for 10 to 100 times less money. It's as simple as this. Now, this energy that we use has another advantage. Doesn't cost us anything. This is oil. It's pretty, no? Don't you think? It's beautiful. I like oil. Actually, this is microorganisms that lived in the ocean 10 million years ago to 500 million years ago. Those microorganisms, as all life on Earth, are full of carbon. They die because they are no more eternal than we are. And a little fraction of these little microorganisms, when they die, fall on the ocean floor. There, they mix up with mineral sediment, namely dust brought by the wind, sediment brought by the rivers, the shells of the little microorganisms that fall down also, etc. All this gets buried in a number of places by tectonics. Therefore, it comes closer to the heat of the center of the Earth, gets slowly cooked in the absence of oxygen. It's a kind of distillation that you have. And the sediment becomes stone. And here you are, you have an oil reservoir. That's an oil field. And that's how an oil field is created. And if you go at the proper place and pump with the proper pump, you get oil. Well, it happens that all this process of going from ocean microorganisms to an oil field, nobody paid a single cent in the room for that. So wind is free, the sun is free, oil is free, coal is free, gas is free. The genetic code of wood, any type of wood, is free. Actually, all natural resources are free. By convention in the economic system, the things without which we wouldn't be on this earth are free by convention in the economic system. It's a major flaw. It's a major flaw. I mean, we depend on a stock that has no price. If you do this in a private company, I can tell you, you go bankrupt. It's exactly what's happening to us, actually, at the planetary scale. We are kind of going bankrupt. And because oil is as free as wind, it's the reason why, historically, we have not shifted from fossil fuels to renewables. We've done exactly the opposite. We have done exactly the opposite. And the reason why is, again, lies in physics. Let's suppose that I take a volume of air which is not very far from the volume of air of this room, say a cube of 10 meters on each side. Let's assume that this wind blows through a windmill at the speed of 80 kilometers per hour. Well, the amount of energy with a yield of 40% of the windmill that you are going to get at the end is the equivalent of what you have in 3 milliliters of oil. On the left, the train leaves the station when there is wind. On the right, the train leaves the station when you have decided that the train is going to leave the station. On the left, when you have to store energy which is coming from a source which is very diffuse like this one, so you have to gather it, collect it, and concentrate it, it's going to need much more work than just to go and dig a hole in the middle of the Saudi desert. Which is why, as all we pay is men, again, nature doesn't get paid. So oil is free, wind is free. All you pay when you pay energy is the amount of labor and revenues to the stockholders that are required in the process of going from a resource which is free to what you pay. Okay, so all you pay is men. And on the left side, you pay much, much more men than on the right. Which is why, on the left, it's going to cost you a couple cents before storage, and anything in the range of 20 to 50 after storage, while on the right, it's a fraction of a cent, storage included. That's physics. That's physics. Because on the right, you have something which nature has already elaborated, very sophisticated, and concentrated at no cost. So if you have to do it with manual work on the left, it's going to cost you an arm. I mean, it is as simple as this, because of the economic convention and because of physics. Which is another way to say right away that I don't believe a single second that we are going to keep the standard of living that we have today on Earth, with 7 billion people and just renewables. You can just forget that. It will never happen. Never. We can live only on renewables with 500 million people and the standard of living that we had 2 centuries ago. That we know because we've already done the experience once. So that we know it's possible. Maybe living with something which is a tenth of the present standard of living with 5 billion people on Earth is something possible. I don't know. But keeping the present standard of living, 1 car for 2 people, 40 square meters of housing, heated in the winter, cooled in the summer, etc. The supermarket packed up with goods, all this with renewable energy, not a single second it's going to happen. Not ever a single second. Okay? Because of this. And that's the reason why, up to now, energies, when we have discovered them, we have progressively piled up one on the other, the energies that we have discovered, meaning the converters that we have discovered, because going from wood to coal and coal to oil, actually we have always gone from an energy to an energy of higher grade, in a way. The best energy you can think of is oil. It's liquid, so you can transport it and store it very easily. It's very dense in terms of energy content and very simple to use. An engine is a small device that you can manufacture in huge quantities. Okay? So you have nothing better than oil. What you can see here is that when you look at the amount of energy, so namely the amount of machines that a man has used on average on Earth for 1.5 centuries, wood is a little special because it was mostly heating. You can see that on top of wood that has slowly decreased, we have put coal. And today, 2/3 of the coal used on Earth is used to produce electricity. You have 2,000 gigawatts of coal-fired power plants on Earth that we should get rid of, by the way, in the 35 years to come. So by the time the youngest in the room are my age, okay? It's about this. We should get rid of 2,000 gigawatts of coal-fired power plants on Earth if we want to stick to the 2-degree objective. 35 years. Get rid of all. Okay. Oil is the energy that you use to move around. Gas has come on top, hydroelectricity has come on top, nuclear has come on top, and now the last thing that has come on top is new renewables. So new renewables is the pink part, and that's the combination of wind, solar, tidal, wave, geothermal, biogas, just name it, I probably forget 1 or 2. Marine currents, whatever. And you see here the contribution in terms of energy supply per capita that new renewables today occupy. Of course, a number of people think that we are going to replace all this by new renewables, again, keeping the standard of living and the low price of energy that we have today. I doubt. The reality today is that 80% of the energy we use on Earth is fossil fuels. The reality today is that if you look at the strongest increase in electricity production over the last 10 years, it is called by far, okay? So that's the reality. And the reason why we do not want all that energy supply to decrease is because of this. With the little equivalence that I've just calculated before, namely one human being equals to 100 kilowatt hours of mechanical power per year, with this, 4 legs, 10 times less for arms, the order of magnitude of the energy supply per capita on Earth, 20,000 kilowatt hours per year, is the mechanical equivalent of 200 slaves per capita. So if fossil fuels did not exist, in order to have the same standard of living on average on Earth, we should need an exoplanet of some kind with 1,400 billion people on it that would cycle all day and send us the mechanical energy so that we can transform what we transform today. In France, the minimum wage worker is closer to 500 to 600, and you in the room, who are generally in the upper classes, you're over 1,000. Those mechanical slaves are the machines that manufacture your clothes, the machines that have manufactured the chairs that you sit on, the machines that have manufactured the buildings you live in and you work in, the machines that have manufactured the food that you eat, the planes that move you around, because I know that researchers take planes all the time, etc., etc. So it's all this. The machines that manufactured your glasses, all these machines combined together, they represent the equivalent of 1,000 slaves working all year round for you. That's the physical reality of our modern world, brought by this. And now you understand that when we want to get rid of all this in the name of preserving a stable climate system, about everybody says yes, but no. Yes, but no. The reason why we have come to a situation where we believe that we are going to achieve the physical goals that we have set up, and in the same time achieve perpetual growth, is because of his pals and himself. This is Jean-Baptiste Say. Jean-Baptiste Say is among the classical economists that 2 centuries ago have designed, have framed the basis of the modern economy. At the time, these people have said explicitly, that's explicitly said into the book that I've mentioned, Traité d'économie politique, he said that natural resources are by convention free. Why did he say that at the time? For something very simple. Again, 2 centuries ago, humanity is 500 million people, life expectancy at birth is 25 years, GDP per capita is ridiculous. So what Jean-Baptiste Say correctly thinks at the time is that a first-order approximation, which is correct, is to say that the decreasing of the natural resources is something which is negligible in terms of obstacle to the economy compared to the lack of human beings able to work or the lack of human capital. In other words, he said if we want to chop down trees and bring them to the cities to heat the cities, we have far enough trees. The only problem is finding enough workers to chop down the trees and finding enough workers to bring the trees to Paris. That's what he thinks, okay? Same thing for, I don't know, digging for iron ore into the first iron mines. I mean, it's just, the limit is not on the resources. The limit is on people able to do the job. And he said, nature is so wide, so tremendous, that decreasing it by just a little bit is something that we can neglect. And if you neglect what you do to nature, it's equivalent, in mathematical terms, to say that it's infinite, and therefore that any diminution is zero, or relative diminution is zero. So he says, depletion of natural stocks is zero. 2 centuries after, we've gone from 500 million to 7 billion. We've increased the individual consumption by anything between 30 to 100. And we still consider that the first order approximation is nature is zero. A valid, sorry, first order approximation is nature is zero. Of course, it's not valid. But thinking like this has led to modern economics, which reason this way, basically. We have a productive system. The two productive factors are human capital and human work. And if we have those productive factors, the supermarket is full of things to buy. That's, no, don't laugh. It's exactly the way they reason. Okay. So in this way of reasoning, we have two exogenous factors, which are capital and work. And GDP is endogenous of these two factors. But energy seen as a commodity, as I said in the beginning, is a product you buy when GDP is there. And so energy is endogenous of GDP. So with this kind of reasoning, first you have enough people able to work and enough human capital, then it triggers more GDP, then it calls more energy. And by the way, that's exactly the way the IPCC scenarios in the stress are designed, which is very funny. I mean, physicists have spent decades setting up models that try to represent correctly the reality, or that account correctly for the physical reality of the climate system, and you feed these models with hypotheses that are totally, out of the real world. Totally out of the real world. We could have listened to somebody else at the time. Let me introduce someone named Charles Dupin, not graduated from this place, only from École Polytechnique, sorry. And in 1827, Charles Dupin calculated the slave equivalent, or rather at the time, the worker equivalent of the productive forces that we had in the country. So he said, okay, in agriculture, we have people able to work, but we have kids. I mean, the population at large is not only men, you have mostly women, counted women for counted children from one half or 1/3 or 1/4, I think it was 1/4. So that leads him to an equivalent for the human part of the productive forces. No, it's okay. I'm going to show you here. Here. Then he said, okay, we also have animals. So I add up the animals, and that's equivalent to a number of workers. And at the end, I come up with the conclusion that the mechanical power that you can put into agriculture, because of, at the time, biological slaves, that is animals, is equivalent to 4 times what we have regarding bodies. And he says we can do the same thing for industry. So I can consider water mills and windmills, etc., as equivalent of human bodies. And that also gives me the productive force of not only the population, but the population and the machines that we were able to master at the time. Okay? So Charles Dupin correctly understands at the time that production is not done by men, production is done by men and machines. And when machines represent much more than men, actually the first order approximation is not I take population and capital, but I take machines and something else. And that's exactly the way to think. Actually, if you have products in the supermarket, you need the raw materials to produce the product, because if you have atoms of copper into something you buy, you have to find the atom of copper somewhere in the environment. Okay? You do not create an atom of copper because you have a credit at the bank. Doesn't work. Okay? So all you can do is find it into the environment. And same thing actually for all the elements of the table of Mendeleev. So if nature had not created for us and for free the 92 elements of the table of Mendeleev, we wouldn't have any cent of GDP. But that's free, again. So we need resources to transform, and we need the ability to transform these resources, namely human beings at the beginning, and now machines and the food of their own, that is energy, which account for 200 if humanity accounts for 1. And there you see that the bottleneck, which is going to have the importance of the first order, is not do we have enough men, but do we have enough energy. That's the true bottleneck. It's the only one to look at. Capital in this system is only an internal loop because you produce a building exactly the way you produce a pair of glasses. You take resources into the environment, transform it with machines and men into something else which we deem more valuable. Okay? It's exactly the same physical process. The only difference is that consumer goods is something that are supposed to be destroyed when you use them, or destroyed pretty fast, whereas capital goods is something that is not destroyed when you use it. But that's the difference. Now, if in this flowchart you have a bottleneck on energy for whatever reason, you might lack energy, or you might decide that you are going to compress the energy supply in the sake of climate. Doesn't make any difference there. You are going to compress the mechanical input of machines, and then you are going to contract the outgoing flow, that is production. Less energy, less consumer goods. We are going to see that in a minute. If you have less resources, it works the same way. It works the same way. And this is the reason why, when you look at the world as a whole, the best macroeconomic model that I have found so far is a straight line. A straight line. On the horizontal axis, you have energy, which is actually the number of machines that we use. And on the vertical axis, you have the economic counterpart of the physical flows that we have created with these machines, namely added values piled up on top of the others, that is the GDP. So this is the logical conclusion of having production devoted to machines that are 200 times more powerful than humanity. You should expect this graph to look like this. And it is a matter of amount, it is not a matter of price. And I've got a second conclusion that might hurt a little economists in this room, if there are some. There is absolutely no such thing as an elasticity between price and volume. You know, a number of people say, okay, you have a product. If you have more of that product, it costs less. And if you have less of that product, it costs more. Wrong answer. This chart is a plot of the amount of oil which is offered on the world market and the price of the barrel of oil. And the dots here begin in 1921. I removed the dots before because otherwise they would have occupied too much space here. And it goes to 2015, but it doesn't make much difference if I had put 2016. If you had had an elasticity, dots should be organized this way. More oil, cheaper, less oil, costlier. Very simple. Okay? What you look at here is anything but that. Actually, it's not bijective to begin with. You give me a price, I can't give you a volume. Actually, if you look at this graph, you can say that the first order approximation is that you have two orthogonal inelastic regimes. One regime in which the volume can do anything it wants and the price remains constant. Then another regime, which is the exact opposite in a way, where the price does anything and the volume remains about constant. Then again, a regime in which the price wobbles a little around a fixed value when the volume is changing a lot. Then again, etc. So there is absolutely no link between the nominal price and the volume. So anybody who is using, and I know economists that do use, an elasticity, a long-term elasticity, because you have a short-term elasticity, but a long-term elasticity between prices and volumes regarding energy or actually any commodity in a model is bound to give you a result which is false, because there is no such relationship. Now, once I've said this, again, the question is, what happens if we go back to the original question? Now, as you have understood, production is not a matter of men being helped by machines. It's a matter of machines being helped by men. The driver of the tractor is only there to guide the tractor. It's not the driver of the tractor which is plowing the earth. It's the tractor. Okay? So if you can remove the driver and replace it by software, you have the same crop. If you remove the tractor and keep the driver, you do not have the same crop. Okay? So it's the machine which is producing. The man is just there to give orders. And that's true for tractors because the power of a tractor is 600 times the power of a pair of legs. The power of a machine of public works is 1,000 times, order of magnitude, the power of the pair of arms that it replaces. So same thing. If you keep the machine and put the software in it, you get the same production. If you remove the machine and keep the driver, you do not really get the same production. It's because of machines like this, plus other machines that I'm going to show, for example, this one, plus the cement factories, again machines, plus the steel mills, again machines, etc., that today we're able to build a tower in La Défense in 1 year, when it took 1 century to build Notre Dame with muscles. Cheap housing is machines. No machines, no cheap housing. Very simple. So droit au logement is a child of energy. No energy, no droit au logement. A train has the same power than 100,000 times the legs of the driver, or 100 times the legs of all the passengers combined. A plane is 1 order of magnitude above because it has to fly. And if you look at the steel mill, precisely, you would require to replace a single steel mill, which can be operated by a single person. You would have to take all the inhabitants of the Île-de-France, put a hammer in their hands, and make them hammer all day. Okay, so you do not study physics here anymore. You hammer steel all day just to replace 1 steel mill if we have no energy. Okay. So these machines, they are tremendous. Now, what happens if we have less machines? Are we going to replace them by men? So if we have less energy, someone can think that we are going to replace machines by men, and that's a good thing for employment. Unfortunately, that's a wrong answer. If you have a machine plus the food of its own, plus the driver of the machine, you have the equivalent, take a tractor, of 600 men. Now let's suppose that you contract the energy supply. That means that you are going to contract the amount of machines that can work, and you say, okay, it's a good thing. I'm going to replace, namely in this example, half of the machine I do not have anymore by 300 men. That would be correct if paying a man was 1 on 300 times paying a machine. Then you have an economic equivalent, and you say, okay, I remove the machine, replace it by 300 men, cost me exactly the same. But it happens that it's not the case. The machine costs you a couple men. So what happens if you have less machines is that first, you're going to have less GDP, because you cannot replace the machine by a productive force which costs you the same thing. And as the man is there only to drive the machine, you have less jobs. So with the tremendous difference between the productivity of a machine and the productivity of men, what we do today if we contract the energy supply in the first order is that we are going to contract at the same time the GDP and the jobs. And I do not only say that, I prove it. This is the energy supply of Spain. The energy supply of Spain peaked in 2007. Who knew it? No one. Okay? It's not in the paper. Putting in service a new windmill is in the paper every day. This is not in the paper. This is much more dramatic for the future of Europe than erecting a new windmill. Much more dramatic, I can tell you. So the energy supply peaked. Why did it peak? Because the energy supply of Spain at the time was mostly oil, and the supply of conventional oil, that is all oil which is not shale oil and tar sands in the world, peaked in 2006. It's not in the paper either, but it's real. So it peaked. So because it peaked, the energy supply coming from oil decreased, and as it was the dominant share of the energy supply of Spain, the energy supply of Spain decreased. Now look at the number of people that work in Spain compared to the population. That's something which should be used instead of the unemployment rate, because the unemployment rate is the fraction of people that wish a job that do not work. But it is not something relevant, because you have to ask the people whether they wish a job or not. This curve here, it's the employment to population ratio, which is the fraction of the population aged of 15 or plus that does work. It's a physical indicator. You do not need to ask the people whether they want a job or not. Because if people don't want a job, because they said that they are tired of looking for a job, or because they said that now they have some kind of training that they believe will provide them a job later on, even if it's not true, etc., you remove them from the unemployment statistics. So there is a very simple way to decrease the rate of unemployment. It's to make so that people do not want a job anymore. Do not laugh. About half of the unemployment in the US was solved this way. Just this way. Okay? So this is the employment to population ratio in Spain. And what you can see is that the fraction of the population that is able to have a job in Spain is far from having regained the level of 2007. Far from having regained that. So if you look at the dynamics, okay, growth is back, but growth is not back so that the situation has become the same. And now look at the GDP. So that's the same curve that I've drawn for the world, but it's for Spain. What you can see is that from 1969 to 2007, well, you have an increasing energy supply, so namely an increasing number of machines at work, so you have a growing GDP. 2007, you reverse the curve. GDP decreases. If I go back to the curve regarding the energy supply, what you can see actually is that you have a rebound starting from 2014, or yes, 2014. And you have the same rebound on jobs and the same rebound on GDP that you can see here. So if you want to know whether electoral promises that depend on the GDP are going to be fulfilled or not, there is a single thing to do, not two, a single thing to do. Look at the provisional supply of energy in the country. If it goes up, you can believe in the promises. If it goes down, just don't believe in the promises. It is as simple as this. As simple as this. Of course, politicians do not know this physical analysis of the economy, so they keep on promising because they don't see the point. We have a minister of energy, 5% of our spendings. They just don't see the point. If I tried to say this to a significant fraction of the political class, they would just laugh. Think I'm mad, or think I'm speaking Hebrew, which I don't. Look at same thing with Greece. Who has never heard of the problems of Greece recently? Somebody? Okay. Same story. The energy supply of Greece is dominantly oil. Oil contracts after 2006. So does the employment rate. So does the GDP. Same story. Look at Portugal. In Portugal, the energy supply stabilizes after 2002, 2003. Well, so does stabilizes. Well, the employment to population ratio decreases a little because the number of jobs remain constant with the population that grows. And the GDP stops to increase. It works very well. Now look at Europe. In Europe, at large, the energy supply comes from oil. Oil, as I said, is the combination, well, not as I said, in Europe is the combination of our domestic production, the North Sea, that peaked in 2000, plus imports that globally peaked in 2005, so 2006, sorry. So the oil supply in Europe has decreased by 16% since 2006. And the trend after a short rebound, which is due to the tremendous increase in the price of oil between 2008 and 2014, which has triggered tremendous investments in the upstream part, which has triggered a rebound in production. Now we are going to witness the exactly reverse process. Low prices of oil, slashing in the upstream investment, decreasing in the production of oil. So this is going to go down again. Gas, if I say gas, I'm sure that many people in this room will think Russia. Wrong answer. 60% of the gas that we use in Europe is coming from the North Sea that peaked in 2005. The imports are about constant in volume because installing a new gas pipe is something that takes 30 years. If you have followed the news, you might have followed the adventure of Nord Stream, 30 years. South Stream, we haven't even given the first shovel to the first worker. So it's going to remain about constant imports. Even if we wanted to extract shale gas, assuming there is shale gas, which we don't know, that would be the upper limit of the supply. Okay, so it's not a game changer. So this is also going to go down for the years for the decades to come. And then coal. Even before coal was a problem for the climate, the domestic production of coal had been slashed by 3 during the last 3 decades because Europe was the first continent to begin to extract coal, and now coal is almost fully depleted in Europe. The only thing that remains is a very poor coal named lignite in Germany, but apart from that, the rest is decreasing rapidly. And as you can see, imports do not increase rapidly because importing coal requires logistical means that are tremendous. You need harbors that are devoted to that, you need trains that are devoted to that, etc. It's not something that you do like this. So, when you look at the energy supply of Europe, which is at the forefront of the energy transition, still, it relies on coal, which has peaked domestically and is decreasing, on oil, which has peaked domestically and partially in the world and declines, on gas, which has peaked domestically and is not that easy to import, on nuclear energy, which has peaked in the mind of people, so we believe that we should get rid of it. And of course, it's not with this thing that we are going to supply the equivalent of all the rest. When you look at the industrial production, you find again things that recall this shape. You see it climbs until 2007, declines and raises a little, or rebounds a little from 2014. Well, look at the construction index in Europe. You have exactly the same thing. In 2007, we have gone through the maximum of the annual the annual volume of construction. Then it has declined, rebounded a little. Same thing, the image has been suppressed. I wanted to show you the traffic of goods in trucks. Same thing, it peaked in 2007 in Europe. And that's the employment to population ratio in Europe. So it lowers less when you have a crisis because of the share of the public sector in Europe, which is higher than, for example, in the US. But still, it has decreased from the maximum in energy supply, a little rebound. And regarding the GDP per capita, it's exactly the same story. This is a curve that shows you the GDP, or rather the increase in the GDP per capita over the last 50 and something years. So in blue, you have the annual change. So this, for example, means that from 60 to 61, the GDP per capita increased by almost 5%. That's for Europe. Okay? From 61 to 62, it was 4%, etc. And in orange, you have the average over 3 periods. The first period is until the oil shocks. Energy per capita was growing rapidly, and GDP per capita was growing rapidly. Then we have the period between the 2 oil shocks of 79 and 2005, where the energy per capita in Europe was about constant. So the amount of machines per capita was constant, and with the exception of the energy efficiency that we could implement in the machines every year. And so the growth of the energy per capita decreased on average to 2%. And from 2007, that is the maximum of the energy supply in Europe, you can see that the GDP per capita has stopped to increase in Europe. Now let's take a zone, which is Europe, in which you have the same production every year. People are free to move around. People are free to move around, and you have the same production and the same, on average, revenue per capita every year. On the western part of Europe, revenues are, on average, 3 to 4 times what they are on the eastern part of Europe. And people are free to move around. What do they do? Well, the Polish plumber goes to London. He contributes to lowering a little the wages in Great Britain. and increasing a little the wages of the average Pole employed wherever he is. Okay? So actually what you do is you progressively erase the difference in potential, in a way. You create a current. But as the energy at large doesn't grow, anything that someone wins is something that somebody else will lose. Okay? And you ask the Brits whether they like it, and they say no. So the Brexit is a direct consequence of the fact that the energy supply has begun to decrease in Europe in 2006, and the Economic Convention believes that it's of no importance. It's a conjunction of the two. Now I'm going to end this with a little rule of three that I am going to bring to you as a way to reflect on the future. I take the jobs that we have in a given zone and I say something that we should all agree on: jobs equal jobs. So far, not Steve Jobs, of course. I divide and multiply the jobs by the GDP. You know that I can always divide and multiply by something which is not nil if I want to do so. Doing this division, I have created here an indicator which is how many jobs can I put into 1 unit of GDP. This means this is actually the reverse of the term GDP on jobs, which is how much money I give to someone who has a job for a given GDP. Okay? So this evolves as the reverse of the wages. If I increase wages, this term decreases. If I decrease wages, this term increases. Or actually not wages, but revenues. Okay? So the less money people earn for a given GDP, and the larger number of jobs I can put into the said GDP, which is the history of negotiations on wages between bosses and employees. And I'm going to divide again and multiply by energy. So this is the energy efficiency of GDP. It's how many euros of added value I can create when I've transformed the environment up to 1 kilowatt hour. Okay, so I transform the environment up to 1 kilowatt hour. This is supposed to create added value, namely if I transform iron ore into a fork. It's more convenient to eat your food with a fork than with a handful of iron ore, obviously. So I've created some value. And so but also I've used some energy. I've changed something. Okay? And the more added value I can create for a given physical flow, and the more efficient my economy is. Of course, you have limits. For example, the Carnot law is a limit for internal combustion engines. You cannot go beyond. Okay? When you want to get iron out of iron ore, which is, if my memory is correct, Fe2O3, you need a given number of atoms of carbon to reduce the oxide. You cannot go beyond or have less or have more. I mean, it's that number and nothing else. So you have a number of physical limits to energy efficiency. Okay? It's not something that you can improve forever. Now, if I look at the past, in the recent past, the energy supply in Europe for the last 10 years, say, has decreased by 1% per year in rough figures. The energy efficiency of the economy, on the other hand, has increased by 1.5% in rough figures. So far, if I take the right part of my equation, the combination of these two is a slight increase of 0.5%. Now, if I want to keep the same job-to-population ratio, that is, the same number of people employed given the population, the number of jobs must change at least at the rate at which the population increases. The population in Europe today is increasing at 0.4% per year. So this is 0.4%, this is 1, minus 1, this is 1.5. My equation is balanced if this doesn't move. So today, to keep the number of jobs constant, the job-to-population ratio constant, I must not grant any increase to people that work. It is very simple. It's not necessarily pleasant, but it is very simple. So every time somebody gets more money for his job, he's creating a small unemployment somewhere. Because it doesn't work that if you have more people into the economy that work, you have more GDP. Again, it's going the other way around. We're in excess of people that want to work today. The limiting factor is the mechanical power and therefore the energy. So first we have a prescribed GDP because of the mechanical power available, and that gives us a given amount of money that we can distribute to people that operate the machines that mean work. Even researchers, they operate machines. You operate computers, you operate planes indirectly, or you benefit from planes, you benefit from cars, you benefit from heaters, you benefit from people that print papers, etc., etc. You're in a world of machines as the rest of the population. So I can create as many jobs as the energy supply allows me to, given the fact that it's the machines that produce. Now I'm going to end with the Paris Agreement. I've got 1 minute left, if I'm correct. Some of you might know this graph. Who knows this graph? Not that many people. Okay. This graph comes from the last IPCC report. Who knows the IPCC? Who doesn't know what the IPCC is, rather? Okay. The IPCC, for which the French equivalent is GIEC, is the International Panel on Climate Change. That is the UN body that has been established in 1988 to assess the available science on the impact of humanity on the climate system. Okay? So what the IPCC does is that it takes all that has been published in the scientific literature and assesses that matter in order to produce reports that represent the state-of-the-art knowledge on the impact of humanity on the climate system. Okay? So this graph comes from the last IPCC report. I think it comes from the technical summary. And it says something which is very simple. Here you have a graph in which you have the cumulated emissions of humanity between pre-industrial times, namely 1850 to make it simple. Doesn't change much if you take 1870. And 2100. Of course, part of it is hypothetical because 2100, as you probably know, is not today. And here you have the global temperature increase between pre-industrial times and 2100 that derive from the cumulated emissions that we have here. And all these curves, they follow time, and depending on time, they give you both the cumulated emissions and the temperature increase in 2100. And they end at different points because it corresponds to different emission scenarios between today and 2100. But the important thing is to know that basically you have a linear relation. So you look at the cumulated emissions. For example, at the end of 2015, the cumulated emissions of humanity was 2,000 gigatons of CO2 equivalent. And that tells you that we have already committed for 1 point something degrees of increase between pre-industrial times and 2100. And as most probably all humanity is not going to die tomorrow and stop emitting tomorrow, it means one first thing is that you can forget the 1.5 degree increase that was in the Paris Agreement. This is about as sound as if I said, when I'm 30, I'm going to do this. Nobody reacts. Okay. I can say it if I want to. Okay, it's of no practical use. If we want to stick to the 2-degree objective, means that the temperature increase is there, and so we can reverse the diagram and say that we have a carbon budget, something that we mustn't go beyond, which is 3,000 gigatons of CO2 equivalent that we are allowed to emit between pre-industrial times and 2100, of which 2,000 have already been emitted. So even if it's late, you can compute, as I can, that 3,000 minus 2,000 equals 1,000. I think we should agree on that also. And that means if we have a budget of 1,000 that remains, that if the path of emissions is something which is more or less continuous and that can even be derived, then it means that we have a checkpoint of dividing the emissions by 3 between now and the time that my kids are my age. Okay? That's what we should do if we want 2 degrees. Now let's go back to my equation. As most of the energy today is fossil fuels, and maybe we are going to discuss of that point, but as physics tell us that it's going to be, I mean, it's very, very improbable that all these fossil fuels is replaced one by renewables and nuclear in the 35 years to come. I mean, it's not fully physically impossible, but it's close to, okay? Because the prerequisites in terms of acceptance of the general population, that everybody works in there, in this program, and nowhere else, doesn't seem very, very, very high. So basically, dividing fossil fuels by 3 is dividing the energy supply by something which is close to 3. And if you compound the interest, it tells you that the energy supply is going to decrease by more than 3% per year. 3 to 4%, okay? When you prolongate that curve, there is no reason that you can see that in the past, it has been rather continuous. And it has been rather continuous in spite of oil shocks that you have here and here. As you can see, doesn't change much, okay? And again, you have barriers. You will not violate the law of Carnot, okay? So the idea that we are going to go from the 1 point something that we have in Europe and actually less than 1% that you have in the world, less than 1%, because in other parts of the world it doesn't increase and can sometimes decrease. It means that the combination of the two is bound, in my view, to be a decrease of something. So if you want to keep that in pace with a population increase that nobody considers that we should stop, by the way, nobody says that, okay? Then if you compound the interest, you give up with the conclusion that you can save the climate, but you will not at the same time save growth and save jobs if you want people to be paid the same thing. If you want to save the climate, people have to accept, which is actually the economic counterpart of the fact that we are going to contract the physical flows and therefore contract production and therefore decrease the purchasing power. That's what it means. And it means also that then people must accept that what they earn is not going to increase year after year, but decrease year after year. Sobriety, in other words, is something that when you look at this simple rule of 3, translates in an obvious way into economics. Okay? And what I believe, that will be my conclusion, is that instead of, that's my father, by the way, instead of counting on a miracle that would allow to have all the goals of the Sustainable Development Goals that we will never achieve altogether, we have come to a time of choosing, so we must choose. Either we say, okay, the fireworks is going to continue for as long as it's able to continue, 1 year, 5 years, 10 years, 20 years. What happens after, we just don't care. That's something which has its internal logic. You can consider that it's not moral, but it has an internal logic. And the other thing that has an internal logic is to say we want to have humanity living as long as it can in the not too bad conditions. And then the obvious conclusion is that we must contract the economy. Today, when you say to an economist what I've just said, again, he looks at you, except for a handful, as if you were mad. The reason why, again, goes back to Jean-Baptiste Say and the fact that with the bases that were thrown on the table at the time, economists have created a system with no apparent limit. There is nothing in the economic theory that says when the GDP is going to reach $70,534 billion, it stops. Doesn't have that. Okay? You have, in physics, somebody who says when you have circled the Earth after P times 12,000 and something kilometers, you have come back to the starting point. You know exactly the value, okay? So you know exactly where the limit is. And in most physical theories, you have this kind of limit that you can express in very precise terms. You have no such thing in the economic theory, and the reason why today, in a way, the worst enemies of preserving the environment are the economists, it's because taking into account the physical limits that come from the environment would oblige them to throw away 2 centuries of accumulated thinking and go back to zero. And they will never do that. Thank you.
Thank you. Your argument for the GDP and energy consumption correlation is quite good, quite convincing. But in the equation, the simple rule of 3 you showed, GDP doesn't feel like a very good measure of, I mean, you're talking about lifestyle, quality of life, but GDP isn't a very good measure of quality of life, I guess. And like, or in your previous graphs, you had a 4-fold increase over 1 or 2 centuries of the energy consumption per capita. But I think compared to 1800, the quality of life by, I don't know how to measure it right, but it has increased more than 4 times. So is it possible to, like, with higher energy efficiency in terms of quality of life per energy, like different lifestyle choices, of course, but some quality of life being high, less energy being used, couldn't you like sustain more well-being with less energy?
There are 2 or 3 questions into your question. So no, it's okay. The first thing is that GDP is a flow and not a stock. Quality of life depends, among other things, on stocks. So the increase of the GDP has gone together with the fact that we have depleted many fish in the ocean, that we have depleted many stocks of fossil fuels, depleted many stocks of ores, etc. You do not account for that depletion into the economic system. I'm going to give you a first answer in economic terms to understand. You probably have heard of the International Space Station. The price tag of the International Space Station is $100 billion. For that price, all you get is a pressure of 1 atmosphere, something that nature has provided for free, breathable air, something that nature has provided for free. You have no gravity for that price, something that nature provides for free here. You have a very basic cycle of water. Okay, so you can drink again what you have just peed. And you have the possibility, you do not freeze. You're protected against the outside temperature, which is not very sympathetic. So that's what you have, basically, for $15 billion per person, because you have 6 inhabitants into the International Space Station. So I can say that the price of the Earth system is at least $15 billion per capita on Earth. At least, okay? At least, because you have that and many more on Earth. You also have grounds on which you can grow potatoes that you do not have into the ISS. You can have fish that you do not have on the ISS. I mean, you have plenty of things. Okay? Today, I can also say that if you look at the rate of depletion of the natural resources, say cultivable land, say forests, say fish, say ores, say fossil fuels, say, I don't know, the CO2 concentration into the atmosphere, the rate of change is generally over 0.1% for anything. I mean, the rate of change for the depletion of fossil fuels is 1% per year, rough figures. The rate of depletion for a number of mineral ores is about is of the same magnitude. The rate of depletion of fish is in the same magnitude, etc. Say I take 0.1% of $15 billion per capita. It means that amortizing the natural capital is at least equivalent to $15 million. At least equivalent to $15 million per capita and per year. And on the other side, you have a GDP per capita which is $15,000, 1,000 times less. So what we are doing right now, you say we're improving our standard of living, I say we're burning the capital. When you destroy what you have inherited from your parents to go and play at the roulette in the casino, you do exactly the same thing. You destroy your capital for a transient increase in your standard of living. That is exactly what we are doing today. You can see it both ways. You can say, I have increased my standard of living, and I can reply, okay, it's not going to last for long because you're basically doing this, destroying your capital. Same thing in my company. If I increase everyone, and in order to do this, I lose money every year, it's not going to last for very long. It's not going to last for very long. So it is because of the economic convention that said that natural resources were free that all economists believe that we have increased our standard of living. We have increased our life expectancy, that's physical. We have increased the size of the population on Earth, that's physical. Okay. We have increased the housing space per capita, okay. Do we have increased the ability to see the future with hope? It's not so sure, okay. So we have gained things and lost things, and I don't, and you can see it both ways.
Couldn't I decide to not play the roulette and go to the beach and enjoy the sunset, and that doesn't
exactly
burn my parents' inheritance?
Okay, it's just
and I'm happy, and my standard of living is good.
So if you do this, you agree to share your room with 9 people coming from Syria, and to no, it's exactly what sobriety is. I mean, you have less and you share. It's exactly what it is. So the equation today is, if we want to last for longer, we have to consume less. It's about this. So that's the answer to the first question. The answer to the second question is GDP is a poor indicator. No, it's a very good indicator of what it represents. That is GDP. GDP has been built, for one thing, to give the economic counterpart of the transformation of the environment that we perform in the course of our productive activities.
Services in GDP.
Yes, but services are not immaterial. Transportation is into services, it consumes huge amounts of energy. IT is into services. It happens that to manufacture computers and the elements of the networks, you emit as much as the world fleet of trucks every year. So believing that services are dematerialized is also something which is a bad term that has been used by journalists. But it's false. The physical reality is that it is totally false. When you plot the energy consumption per capita in countries against the fraction of services into the activity, you have a very strong positive correlation. And another reason why is that in order to have a large fraction of services, you need huge amounts of physical flows, because otherwise you do not need these services. Let me take an example. If you manufacture 1 car per year, very quickly you can get rid of all the insurance sector regarding cars. Very quickly you can get rid of all the bankers regarding lending credit for cars. Very quickly you can get rid of all the people that teach people to drive, etc., etc. So the idea that services can have a standalone life, separated from the industrial bit, no, but it's just what I'm explaining. So it's a coupled system, and in a coupled system, it's the same thing. It's the same joke that with my brain at the beginning. You cannot remove one part and say the other part is going to stay the same. Doesn't work. And services have appeared because we have tremendous industrial flows, because of that. Let me put it the other way around. Suppose tomorrow morning I suppress the world network. Okay, tomorrow morning, no more computers. Do you believe that we will still manufacture as many cars, sell as many cars, have as many planes flying in the sky, as many boats boarding goods in the harbors, as many factories running, etc., etc.? Of course not. Of course not. Because to begin with, you have no banks anymore. Banks today are computer services. Okay, you have no banks anymore. So the idea that dematerialized services replace material services is totally false when you look at the physical reality. Actually, most of the time, they help the industrial sector to thrive. Most of the time. And to finish with this, yeah, GDP, you know, was invented to count tables and chairs and cars and things like this. So actually, it's, as Marcel Boiteau said, money is what we have invented to compare a number of things that are not comparable. So basically, we have given a value to all these things and piled all this up, and that's the GDP. That's what it measures and nothing else and nothing more. And if you correctly account for inflation, which is today roughly done for common goods, not done at all for assets, if you correctly account, because most of the GDP increase of the last 10 years is inflation of assets. That is not discounted into the calculation of the GDP. But if you correctly discount inflation, the GDP reflects basically the number of things that people can buy, basically. So if you have less GDP, they can buy less things. And now the good question is, how do you organize the society so that you still have a reasonably peaceful context with this?
Good evening. You have shown us different curves with the GDP versus the energy consumption with a linear relationship. But for example, in a country like Denmark, the GDP has doubled since the 70s without increase in the energy consumption. So how do you account for it in your models?
Because the boundaries are not the same. The energy consumption is something which is domestic. The GDP takes into account physical flows that happen outside Denmark. When Maersk operates a boat that goes from Brazil to, let's say, South Africa, part of the revenues that come from operating this boat are located into Denmark, but the energy consumption that allows this revenue to exist is located outside Denmark. So when you have a small country, sorry to say small for Denmark, but when you have a small country which is very open to international trade, which is the case for Denmark, and by the way, also the case for Sweden, another country that I know pretty well, regarding its economic frame, you can have, and Switzerland is exactly the same, you can have money that pours into the country, but the energy that pours somewhere else. Which is why the cost-to-consequence relation, because it's a cost-to-consequence. First you have energy, then you have GDP, because you can transform. Is a straight line for the world as a whole, because we do not have trade with Mars. So the boundaries are the same for energy and for the GDP. When you look at a single country, this is something which is valid if trade is something which is in relative proportions small compared to the economy of the country, and if it is reasonably stable over time, which is why I have chosen the Southern Europe countries. And if there is also a very rapid change that does not have, because what you have mentioned for Denmark was a continuous change. Okay, it didn't occur overnight. What I showed for Spain, Portugal, and Greece is closer to an overnight change. I was doing this, does this. Okay. So then it's valid to show that you can see the effect. When it's something which is much more progressive, you can keep the revenues of Maersk within Denmark, or Rockwool, or whatever, and have the flows that give way to these revenues outside. And you can see a number of other countries on Earth, I didn't show them tonight, in which the energy efficiency of the economy degraded over the last 50 years. Actually, it's the case in Spain. It's also the case, if I'm correct, in Philippines, in Thailand, in Vietnam, in Turkey, well, a number of countries have done the, and in the non-OECD zone, the energy efficiency of the economy has changed by only 5% during the last 50 years. 5% overall, not per year. Okay? So there is no written rule that says that energy efficiency should improve over time. I mean, it depends. You have to look at precise cases.
Okay, yes, you have shown the curve with energy and GDP for Spain, and I wondered, you spoke about the time around the crisis, the time of the 2008 crisis, where there was a peak, and I was wondering about the direction of causality between the decrease in GDP and the decrease in energy consumption, because you could also say, well, yeah, and also, second question is about the curve, the linear relationship. It seemed that at the top of the curve, the GDP was doing some very odd curving around. Yeah, I was wondering if you could give an explanation.
The peak is 2007. Here, if you look at the GDP, actually the inflection point is 2007, but the maximum GDP on the vertical axis is 2008. And the fact that the curve is, in quotes, turning left, means that it's first the energy that slows down, then the GDP that slows down. So if I had shown two curves, energy and GDP, both normalized, because I have that also, you would have seen that there is a 1 year lag between the peak of the energy and the peak of GDP. So it's clearly, and it's easy to understand in physical terms. If you have, actually it's a coupled system also. If you have more energy, you can transform more things and create more GDP. If you have more GDP, it means that you have more things, and among those things, you can have investments that allow you to extract faster the remaining energy. So it's a coupled system. But if you look at, if you perform things that look like Granger causality test, you will see that over time, it's mostly energy that drives the GDP. And the thing which is absolutely certain is that with that 200 ratio between the power of machines and the power of men, you can easily understand that if you deprive machines of energy, you will deprive the GDP of part of what it was. I mean, it's obvious.
Thank you very much.